Alright students, Coach Primo here. Yes, I don't have my mask on. That's because no one's in the classroom, so all good. I want to talk to you about our Carnival Project. I'm going to introduce you to it, and I want you to understand that this Carnival Project encompasses two major grades, and they're due next week, both of them. Okay, today is Thursday, October 29th, 2020, and we just finished the probability unit. We just took a test on probability, and you're thinking, I should be done with probability. But unfortunately, we need to have two more grades out of this. And this is the first major project you've had all year, and it goes in the third marking period. So we're going to start in the second marking period by introducing it. And if you finish it in this marking period, great. The grade still goes in the third marking period. So I want you to understand that all the grades you have done already, for the second marking period, are done. You should have completed them already. Some of you are still trying to finish that. Take your time, finish it. You got till Friday, okay? So anyway, let's talk about the difference between theoretical and empirical probability, or experimental probability. Empirical simply means that it was gained through experience. Experimental means the same thing. So what's the difference between theoretical probability and empirical or experimental probability? Theoretical probability is what we think will happen. Okay? Experimental probability is what actually happens. So let me explain what that means. All right, so theoretical probability, we've talked about a lot. We have been discussing tree diagrams and equal likelihood, and this is all based on the theory that if things happen a certain way and everything's equally likely, we know that a percentage, exactly what percentage is going to actually happen. So, for instance, you flip a coin, 50% of the time you should get heads and 50% of the time you should get tails, right? Well, that's theory. That's based on equal likelihood. So in theory, we should get about 50% heads and 50% tails based on the knowledge that there's only two opportunities. So there's two possibilities, and if there's two possibilities, that's our sample size, that's our population, that's our denominator in the probability. And the two different options, heads or tails, are one each. So you've got one half of the time you should get heads and one half of the time you should get tails. Well, that's all based on theory. If you do experiments with flipping a coin, you may find that 17 of 30 are heads and 13 of 30 are tails. In which case then, experimentally, it's not 50%. So that's the difference. It's actually what we think will happen based on the theory and what actually happens based on our experiment or our experience. All right, experiential data, experimental data, empirical data, whatever you want to call it, that's all based on the experiment of it actually happening. Okay, so we need to understand that before we start this project. The project is going to be a combination of different things, and we're going to be able to calculate the theoretical probability of each one. For instance, a spinner. If you get a spinner, and there are spinners online, for those of you that are working online, and we have links to all that. If you get a spinner where you have 5 different pie sizes on a spinner, and each one of those pie sizes equal size, we can theorize that spinning a spinner, it should land on one of those pie sizes 1/5 of the time. Each one of them should have the same exact theoretical probability, 1/5. But through the experiment of going and doing this spinner, we may find that one of them actually has more likelihood of being landed upon with the spinner than the others. We may find that if we have red, white, blue, green, and purple, that the purple gets landed on twice as often as the rest of them. Okay, so it may be something to do with the way the spinner is created. It may be faultily created and not give each one an equal likelihood. Same thing with dice. When you roll dice, rolling a dice gives you an opportunity. If you roll one dice, you have 6 sides. A cube is 6 sides. So getting a 1, a 2, a 3, a 4, or 5, or a 6 is 1/6 theoretically. But you may roll the dice and find out that the 6 lands more often than anything else based on experiments. And the same thing is with cards. When you're playing cards, cards have 52 cards in the deck. Most standardized playing cards have 52. If you add the jokers, it's 54. But each card is distinguishable from every other card in the deck. Some of them are hearts, some of them are clubs, some of them are spades, and some of them are diamonds. The diamonds and hearts are red, and the clubs and spades are black. And then you have the 13 different types of cards in each suit. Those suits we just mentioned are diamonds, hearts, spades, and clubs. So there's 4 suits. There's 2 colors. The diamonds and hearts are red. The clubs and the spades are black. Then there's 13 cards in each suit. And you have the ace, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. Then you have 10, jack, queen, king. Okay? So there's 13 total cards. Notice that the face cards, jack through king, do not really have any value to them. But they are placed in value order. A jack is higher than a 10, lower than a queen. A queen is higher than a jack, lower than a king. And a king is actually higher than a queen, but lower than an ace. Notice I put an ace all the way down by the 2, because it is a value of 1. But it also holds a value of 13. Watch, I don't know how to explain that, 14. It's higher than that's beside the point. The point being is, if we're talking about values in predictability or probability, that's a different story, okay? You're welcome to do that. It's entirely up to you on how you want to do that. But in the meantime, I want you to understand that, so for instance, theoretically, to pull a heart out of a deck of 52 is 1/13th of an opportunity, because, 1/4 of an opportunity, because there's 4 suits. To pull a red card out of the deck, whether it be heart or diamond, it doesn't matter, a red card, it's 1/2. To pull a club, it's 1/4. To pull a 10 is 4 out of 52, or 2 out of 26, or 1 out of 13. Okay, because there's 4 twos, 4 suits, each one has the same card in it, just a different suit attached to it. So you have to understand, in theory, it has to do with how many possibilities, or how many probable out of how many possible. And I'm going to write that down just so you remember that the probability, to calculate probability, and I've done this in class several times, is the number probable out of the number possible. Okay? So we need to think of it from the perspective of what is possible. Okay, if we're talking about we want to get hearts, how many hearts are there? Okay, well, that's probable. There are 13 hearts in a deck of 52, so we have 13 probable. 13. Okay, there's 13 hearts out of 52 in cards. Okay? And we can go further and say lots of things. So, for instance, let's say we're spinning 2 dice. Okay? Well, how do we determine how many different dice rolls there are? Well, there's a chart online. It's very simple to find. But you have one dice, okay, is 1 through 6. And another dice is also 1 through 6. Well, if there's 6 for each, the number possible is 6 times 6. 2 events, the number of each event multiplies fundamental counting principle. We talked about that, okay? Fundamental counting principle is you take the 2 events, the number of each event, you multiply through, and that's how you found the total possible. So there's 36 total possible. Now we need to know total probable. So how many opportunities are there to get 1 on 2 dice rolls? 0, because each dice has the lower limit of 1. So the lowest possible is 2. So we're going to set up our grid like this with 36. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we're going to go 2. See the dice. 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. And we can easily determine by doing this chart how many of each we got. So How many times do we get 1? 1 and 1. Each one of these is 1 time. So we got 2 and 1. We're going to add this up. How much does it add? This is 2. This is 3. This is 4, 5, 6, 7. Okay? And we'll do this all the way through. 3, 4, 5, 6, 7, 8. 4, 5, 6, 7, 8, 9. 5, 6, 7, 8, 9, 10, because 6 and 4 is 10. You see what I'm doing here? And then 7, 8, 9, 10, 11, 12. Now this chart helps us determine exactly how many of each possibility we have. Okay? So if you look carefully, you'll see that 7, running through that diagonal, has the most opportunity to happen. But we can count how many of each we have an opportunity for. So how many times can we get 2? That's 1 out of 36. Probability of 2 is 1 out of 36. Probability of 3, 1, 2. That's 2 out of 36. Probability of 4, 1, 2, 3, 3 out of 36. And you can see it goes all the way up to probability of 12, which is also 1 out of 36. It goes up until we get to 7, which there's 6 out of 36, or 1/6 chance, okay? So, I want you to be able to see this. That chart is actually available online, and I need you to go ahead and take a look at that. So, you're going to have an opportunity to make a combination project. Your probability is based on 2 or 3 combinations. And notice that when you have multiple events, you have to multiply through the events. And if you have multiples of multiples, dice rolls, 2 dice rolls, playing cards, and you're going to do several playing cards things, the more complicated and the more the probability is going to be less than. So in the meantime, I want you guys to go ahead and take a look. I've got more to talk about this, and I'm going to do that on my computer. So let's go there. Now that I've got the introduction done for your project, let's look at what we're talking about. So if you're watching my screen, I've got a lot more things. I have, several periods of classes in here, but let's just go to one class in particular, and I want you to be able to find where the assignment is for the project. So it's in marking period 3. Notice we're completed with marking period 1. I left marking period 2 still in progress because some of you realize that Friday has not come yet. Anyway, let's go into marking period 3. It's going to pull you up, and the only thing there right now are the Carnival game projects. There's a part 1, which is the first major grade, which is due next week on either Monday or Tuesday, depending on which day your class is. And part 2, which is the presentation part of it, which is due Thursday or Friday next week. You should be able to get anything you have from this information in the 3 days we have. Okay, so let's go to Carnival Game Project Part 1, and we'll look at it carefully and see exactly what we're talking about. So as you notice, it comes up. This is the part of the whole thing. The description is all written out for you. And actually, this description is exactly what you're going to be doing. So you already know the probability can sometimes be easily predicted. On the spinner below, you could spin a 1, a 2, a 3, or a 4. Or you could say green, yellow, red, or blue. It really doesn't matter. They're all the possible outcomes. Because the area represented by each number is the same, in other words, each pie has the same size, each outcome is equally likely. So the probability of the spinning the number 3 or any other number is on the spinner is 1/4 or 1/4. That means on the average, we expect 1 of the 4 spots to be 1/4 of all spins. They should result in landing on 3 or 1 or 4 or 2. The probability can also be expressed as a decimal, 0.25, or a percent, 25%. We can represent the probability with an area model like this, which this is actually an area model itself. It's just a circle. Or a tree diagram. As you can see, the spinner roll, this is the event, and these are the 4 possibilities. If you're rolling a 1, the probability of rolling a 1 out of the 4 is 1/4. So 1A, conduct an experiment that uses one number cube labeled 1 to 6 to determine the experimental probability of rolling each of the numbers. Be sure to roll the dice at least 50 times. And we have a link here that takes you to a dice roller. And as you can see, it takes you right to random.org, and you can roll it. You rolled one die, got a 6. Roll it again. This time I got a 4. This time I rolled it again, I got a 2. This time I rolled it again, I got a 3. This time I rolled it again, and I got a 3 again. So as you can see, it's pretty simple, okay? So we'll take the total number of rolls. You don't have to limit yourself to 50, but you have to document each one, okay? So the way you do that is you're going to put, well, how many times you roll number 1. I would take a piece of paper and a pencil, and I would put 1 through 5 and make tally marks every time you roll one of those numbers. And then you can put them in here, okay? Now, this is not editable because it's just a description, but down at the bottom, you'll see that you have a link to your own copy of this specific file. Using a model of your choice, determine the theoretical probability of rolling each number on the dice. And you can make a tree diagram or an area model, it doesn't matter. And you'll have your theoretical probability. And you conduct an experiment that uses 2 coins to determine the experimental probability of getting a specific number of heads. Be sure to flip the coins at least 50 times, okay? This has a 2-coin flip, okay? And it'll let you flip it 2 coins, okay? Wonderful. It already has it up there, so it's not seeing it. So we're going to flip. These are 50-cent half dollars. So this time I flipped a tail and a head. This time I flipped a head and a tail. And make sure you mark them this way too. So if you get the first coin head and the second coin tail, mark it that way. If you get the first coin tail and the second coin head, mark it that way. It's very important you do that because you need to see it in a tree diagram or an area model presentation also. Theoretically, we should get 1 out of 4 both heads, 1 out of 4 both tails, and 2 out of 4, or 1/2 of the time, 1 heads and 1 tail. That's just like binomial probability with making a basket, like the assignment we had, okay? Or the review, if you remember the review. So let's go back to the project again. I'm going to go ahead and I'm going to turn these off because they cause problems when I try to go back. You're going to make a model of your choice. You're going to do the theoretical probability of rolling each the heads combination. It says rolling each number on the dice. It should be something else. It should say flips of the coins. And then the last one, we're going to do experiment that uses decks of cards to determine the experimental probability of your choice. What are you using to determine? Number, suit, color. So as I explained, cards have different colors. Cards have different suits. Cards have different numbers or values or face card values, whatever. How many total cards are there? Well, like I said, if you don't have jokers, there's 52 cards in a standard deck. Now, you don't have to use a standard deck. You could use an Uno deck, which there's a lot more cards, which make the probability a lot harder to calculate. Because then you would have to determine exactly how many of each kind of card you have. And that takes a little bit of time. Not impossible, but if you feel like you need to do that, absolutely, by all means, do it. So, and you'll do the experimental probability and the theoretical probability, and you're going to go ahead and do it. Finally, the last thing you'll do is 2 dice roller, and we kind of discussed this a little bit. And we'll talk about the theoretical probability based on this combination screen, and we'll get all that done. The best part about the first part of the project is you're going to make your own copy right here. Let me move my big old mug out the way. You're going to use this link right here to make your own copy of this directions, and all you do is fill it out. Now, as far as making your copy of the tree diagram or the area model, that's fine if you want to do that. It's not in here, but you might want to consider doing a Venn diagram too. That may be more complicated, but I mean, if that's what you're comfortable with, then by all means do it. All right. So meantime, I'm going to go ahead and let you get started on this. This is part 1 of the project. We'll have another video for part 2. And in the meantime, y'all be blessed and be a blessing.